Hey there, awesome physics students. Let's talk about RC circuits. In particular, I want to talk about why do the voltage versus time graph and the current versus time graph, when discharging a capacitor, why do they look the way they do? And I want to give you some intuition about why that is. Okay, so the R and C in these circuits are a resistor and a capacitor, and that's what we have here. We have initially charged up this capacitor, and at t equals 0, we're going to say the voltage that this capacitor is charged up is V naught. And we're going to connect this switch at t equals 0, and then that's going to give a path for the charge to flow and discharge this capacitor. And what we want to do is we want to follow the current and the voltage in this circuit. And first I want you to notice that if I close the switch, the voltage across the capacitor is the same as the voltage across the resistor. Okay? So it doesn't matter which one I'm talking about. So let's plot the voltage across the resistor, which is the same as the voltage across the capacitor, versus time. And let's also plot the current through the resistor versus time. Okay? Now, we know that when you throw this, it's going to start off at V naught, right? Because that's the voltage across the capacitor, and that's going to be the voltage across the resistor. When that happens, that voltage across R is going to give a motivation for a current to flow. So current is going to flow, and that's going to allow positive charge from this side to flow around here and combine with the negative charge, and that's going to reduce the charge on this capacitor as we go. Okay, so we're going to start off with some initial V naught and some initial I naught here, some initial current here. The question is, where do we go from here? Does this increase, decrease, or stay the same? Well, let's see. As the charge here travels from one side to the other, that causes Q on the capacitor to reduce. Well, what effect does that have? Well, for a resistor, we know that they follow Ohm's law. So I equals V over R. That's pretty straightforward. But we can't use Ohm's law for capacitors. Instead, they have their own law, right? Because C equals Q over V. That is, V and Q are proportional to each other. So V is, if I just rearrange this, V is equal to Q over C. So if Q reduces on this, that means that V for the capacitor will also reduce, right? And if V reduces, then these two facts conspire and make the current that is output, the motivation for the current to flow, decreases. Okay, so let's go ahead and take note of these. As Q reduces, because of the current, V reduces. And so as V reduces, I reduces. Okay, then but remember that that I is still greater than 0. It's still not 0. It's still positive. So because of that, this I will cause Q to reduce more. I is still flowing, so that's still causing the Q to reduce. That reduction in Q, because Q and V are proportional to each other, that will cause V to reduce. That V reduction reduces the motivation, so that V reduces. That V reduction will cause the current to decrease, because the motivation for the current to flow is the voltage difference. So the current decreases. But then again, I is still flowing. And so this feeds back and discharges more of the Q. And so what happens is you get a reduction like this. And it follows an exponential decay curve like this. Okay? Now, how do I know it's an exponential decay curve and not something else? Well, if I look at the connection here, I know that V is equal to Q over C, right? From this expression here. But I also know that the voltage across the capacitor and the resistor are the same. And so I can use this. This is IR, Ohm's law, for the resistor. Well, remember that I is the rate at which the charge is transferred. So if I put those two together, I get something that looks like Q is proportional to the rate at which Q is changing. And in fact, Q is decreasing. That's why I'm getting a decrease here. And anytime you get a proportionality equation with the rate at which a thing is changing is proportional to the amount of the thing itself, you get an exponential decay or an exponential increase. In this case, it's a decay. So this tells you why it's exponential and why it has that shape. There's one more thing I want to point out here. What is this initial current equal to? Well, you can look here. That's going to be the initial voltage divided by the resistance of the resistor. So we know what the value of the initial current is. That's set by the initial charge voltage, and we can charge it to whatever we want. So that controls the sort of peak height of this equation. Now there are some things that stay the same about these equations, and I'll have to talk about that in a separate video.